Now, all right, all of you have been back. Is it 21 or 21? Two more coming. Just double check. Wang Niklon still not fine, is it? Oh, yeah, I can see your name. Now, so before we start, we would like to check your understanding, right, of the calculations of delta H of the reaction by doing this one, right? This is the self-heating can, where if I just said before to you, it is like it can be made commercial. Okay, I just recall my times while I was in secondary 6. Okay, so I work with some secondary school students to take part in, I forgot what is that, a chemistry Olympiad, and as well as HASBCC. Okay, this and while HASBCC is the first year, okay, of organizing that activity, that competition. So this is one of our awarded topic. Okay, so we design two applications. One is self-heating can, the other one is the cooling pack, in which both of them involving the two chemical reactions. Okay, so one in which it will give out a lot of heat, the other one with cooling effect. Okay, so I would like to show you what is that. Okay, of course, I don't know whether or not I can find my video in my time, but I have got that maybe in my office. So we were once taking the video, okay, in 20 years ago, right? So 20 years, wrong calculations, I don't know. Anyway, so the video, they will show my times, and also some of our secondary school students try to introducing the topic, like how we can design the self-heating can, how we do the cool pack, and how will you analyze the data. Okay, so it is our application, and indeed, I don't know whether or not it is my our design is just a pioneer of those, or you just indeed having some other countries or places where you have already got that design. But anyway, you may see in some places just like Japan, and nowadays we have got the self-heating can, in which what a coincidence is that it is the heating relies on the quicklime and the water reaction. So you know that calcium oxide and reacts with water to give out a lot of heat. Okay, so this is the design one, which will help heat up the coffee. Can you see that? So this one, we have got the reaction, and the heat will be transferred from the reaction vessel to the coffee, such that the coffee will be heated. Okay, so how can I mix that too? Indeed, we have got we've got an isolation beforehand between water and the calcium oxide. So what do the customer do? Could you please see that? We have got a pin here. It is used to pierce through the plastic bag of water, okay, such that it can get mixed with the calcium oxide underneath. By doing so, the reaction has started, and heat will be transferred from the hotter place to the cooler place. So it is hotter, right? The reaction measure is hotter while the coffee is cooler. It will be something like that. Okay, so this is what you may know about the self-heating can. Spend some time on doing this. First of all, and I would like to check the answer about 5 minutes. Okay, do it now. Now, for the time being, I would like to check the video with you. On one on exothermic reaction and one on endothermic reaction.
I am going to do today 2 experiments to demonstrate the exothermic and endothermic chemical reactions. So, first we are going to do an endothermic reaction where I add barium hydroxide and ammonium chloride together. So I'm going to put some barium hydroxide in this beaker. And in another beaker, I will add ammonium chloride. Okay. Before adding these two reactants together, I'm going to use a piece of wood and I'm going to make it wet. So I'll pour some water on it. Now I'll place the beaker containing the barium hydroxide. I'm placing the temperature sensor to record the temperature before the beginning of the chemical reaction. It is now around 24 degrees Celsius. So now I'm going to add the the ammonium chloride. The reaction is very fast. The temperature started to drop. It's going to go below 0. At this point, water will freeze. So it's like a white liquid now. And the beaker is very cold. The temperature keeps on dropping. It is really cold. So now after the reaction finished, I'm going to lift this up, and I expect the water that was between the beaker and the piece of wood froze. So no matter how I hardly try to separate them, it's just sticking. This is some water fell so here. Okay, I'll try to keep it for a while. Okay, so here we go. The water that was between the beaker turned to ice. See the pieces of ice? This is an endothermic reaction. This reaction absorbed the heat that was in the water and turned the water from liquid to solid. Now the second experiment is to show an exothermic chemical reaction. I have here calcium carbonate, and I'm going to add concentrated sulfuric acid to it. So first we're recording the temperature.
So I just show you one of the endothermic reaction. Now I do think the reaction between quicklime and water will be more exothermic, so I just skip it. Now, do you realize do you know the reaction involved about the endothermic reaction, the highly endothermic reaction that they just mentioned, the highly endothermic reaction. So what are the two chemicals involved? Do you still remember? Could you please type it in the chat box or just say it loudly? Tell me what are the two. What are the two chemicals involved? Lý Thịnh. Lý Thịnh, do you know what are the two chemicals that we have just mentioned? Oh, sodium hydroxide and ammonium chloride, is it? Is it sodium hydroxide? Barium hydroxide. Yes, that's right. Barium hydroxide. So the reaction involving barium hydroxide and what? Ammonium chloride. So this is the very exothermic reaction. While in my times I chose barium hydroxide the same, but I will use this one, ammonium thiocyanate. But anyway, the general reaction is more or less similar. Okay, it's because it will have a reaction between like this. We've got barium chloride. Okay, we have got ammonia gas and water. So it is a highly endothermic reaction. Okay, it's a highly endothermic reaction like this. So you may need to adjust a little bit about the balancing equation. Can you manage the balancing equation? Is it? What else? What else should be balanced?
Chloride.
All right. Yeah, you have got two, right? Is it two here? And ammonia is two here, right? Isn't it? All balanced? Okay, anyway, I'll leave you guys to try on that balancing equation. Now, my focus simply is that you may experience a very rapid temperature drop, okay, on this reaction in which the heat will be transferred from water back to the reaction vessel. Okay, so heat absorbed from the surroundings, so cool that it will be a drop to -10, right, degrees Celsius, so that the temperature there is cool enough to freeze, okay, to freeze water to ice. So that's why you have got a thin film of ice afterwards, which is found underneath the reaction measure. So this is we try to make this change the design a little bit to make a pack, the pad, okay, which in which we will call that a fever eliminator, as I recall my times, right? We will name that product like this. So funny, right? So you may see the two chemical reactions. One is highly endothermic, one is highly exothermic. Well, this one is rather cheap because calcium oxide can be is a very cheap chemicals, okay, easy to obtain. So my questions for you is on these three. Okay, anyone have a try on that? How about question one? Give advantage of using this self-heating can. So that questions would ask something about the design itself, okay? The design itself. What's so good about this design? So it is something about the commercial product. Is about if you want to get the hot drinks, which is so available whenever you are going to want to have a heat apply, just pierce through the plastic bag, and the hot drinks can be easily obtained. Okay. So this is something about commercial, the marketing approach. Okay. So especially while we do not need to heat it by, for example, burning fuel, electricity, right? So which means that it is rather portable, right? You may see that design is rather portable. Okay, that can be carried from one place to another. Okay, so that's the place of having this hot drink will not be limited. Will not be limited by the source of heating. Okay, because the source of heating is already inside the package. Okay, so you need not take too care of where you can get the stove, where you can get the electricity supply, etc. You may think of some other advantage. Number two, the enthalpy change of reaction of calcium oxide and water is this. And calculate the amount of heat required to warm 210 cm cube of coffee by 40 degrees. Anyone who have got the answer? Okay, you may type in the chat box, or you just turn on mic and tell me. 35.12 kilojoule. So check the sig. It's about what? It's about, it will be in MC delta T, right? You are going to calculate MC delta T for 2A. The heat evolved, it is MC delta T, while MC delta T all refers to water. So you may find in the coffee, okay? So you try to find a coffee, right? All those they were just mentioned. So you may put that data there, right? Get substitution of all things about coffee, because the heat evolved will be all absorbed by coffee. I'll just skip one more point here. Okay, so the heat absorbed by the coffee. Okay, so it is all those that are coffee. MC delta T, M is 210 gram the density of coffee, it is assumed to be equal to that of water. How about C? C is specific heat capacity of coffee. While the temperature rise, it is 40 degrees Celsius, which means 40 Kelvin. So we may get it about 35,000 something, right? 33,000 something. So because it is roughly 2 sec only, so it is roughly equals 35. About 35 kilojoule. Okay. How about B? Calculate minimum amounts of calcium oxide can for the can to function as specified. You are going to calculate backward. What is the amount of calcium oxide needed? Do you know the answer? With that certain amount of calcium oxide, the heat involved is 35 kilojoule. But you know that 1 mole. Now you take a look on this equation, kilojoule per mole, minus 82, which means that per mole of what? Per mole of that equation listed, right? So you may know that per mole of calcium oxide needed, it release 84 kilojoule of heat. So how would you get the number of moles of calcium oxide? Now, for those who know the answer, could you please turn on the mic? Tell me how you calculate next. Yeah, sorry. I can hear some of you turn on mic. Doesn't matter. We just
find the number of moles of calcium oxide needed first.
Yep, calculate number of moles of calcium oxide needed. So what is that?
So 35 over 82.
35 kilojoule, okay, over 82 kilojoule per mole. Now, so this time we have omitted the minus sign here. Yeah, where here? We omit the minus sign here in the calculations because the minus sign here refers to heat is released. So because we try to get the we try to get the ratio, right? We try to get the relative number of moles of calcium oxide. You just skip that minus sign. So it is no need to have 1 mole, right? About half mole. It is calculated as 0.4, to be more exact, it is 0.428 because it is now in 2 sec fact. Okay, so it is roughly equals to this, okay? 0.43. What's next? So you're going to calculate the mass. Because I've got mole already. How you change it to mass? Times something, right? I don't want mole, I want mass. Gram per mole. So you know what's that? Yes, the molar mass of calcium oxide. So it is 56.1. So what is the answer? So what is the answer? About 24 gram. Isn't it? Okay, about 24 gram. Okay. So this is what, of course, this one, you call it minimum mass. Minimum mass. But of course, in the commercial product, we would need to have more than 24 grams. Do you know why? Do you know why? Deng Junhei, do you know why? In a commercial product, that even though for the businessmen who are so calculating, they would not put it as 24 grams. They would have putting the calcium oxide more than 24 grams.
To ensure all the chemicals has been reacted.
To ensure all chemicals have been reacted. This time I add more chemical. Now take a look at the design. I give you one clue. Take a look at the design. If we are, what do you think? The calcium oxide added should be more than 24 grams minimum, right? Minimum, which means that it's the least amount of calcium oxide. Do you know?
Yes.
Do you know the reason?
Can you ask again?
My question is, you have got the questions asking about minimum mass of calcium oxide, but in commercial product, usually they will add slightly more than 24 grams of calcium oxide inside. Do you know why?
There is heat loss to surroundings, so the heat transferred to the coffee and may not be exactly with the calculated value.
Some heat will be lost through here, right? Through here, right? Through other side. So which will make the heating effect here will be affected. Okay. So so will be less heat will be transferred to the coffee. So of course that for this calculations is based on one assumption. Now I try to take a look at the design once again. So for this it is no problem. For here is also no problem because the coffee is still here. Now take a look on that design very carefully, to be more exact. Here, the coffee is here. The coffee is here. So they have made the design already such that the reaction vector here, the heat will be transferred to here, right? But because of the can, the material also absorb heat. The lid here, right? The heat will also be lost through convection, okay, etc. So altogether, if the businessman have made the claim on the package that it can be the heating effect can be risen more than up to 40 degrees, but finally it turns to less than 40 degrees, this is problematic. They will bring about some legal issues, for example, right? So because the overall calculations based on one assumption, okay, is that all heat released from the reaction will be totally transferred to coffee. So they would add a little bit more calcium oxide to it, so as to protect their claim that the can of a coffee can be heated to have a 40 temperature degrees rise. So that's why I just said in commercial product that maybe add more. And number 3, the reaction of calcium oxide and water, that one, the possible explanation for using calcium oxide in this self-heating can. Can you think of one reason? Now I would like to have 2 people who say the possible reason. One is Mark and the other one is Lim Seng-Han.
Because the reaction is highly exothermic.
Yep, the reaction. This reaction is highly exothermic. The reaction between calcium oxide and H2O is highly exothermic. So of course, it is something about its function, right? I need to get a highly exothermic reaction to heat the coffee. What is the second reason? Why would you choose? We have got so many. Yes, low cost, because calcium oxide is rather inexpensive. It's not so so expensive for the material. It's rather it's not so expensive, so it's easy to obtain. So that's why we would tend to use this one. And of course, you may think of more, something about environmental issues, because while you dump it, it will cause less harm to the environment, because anyway, what is this waste? Water waste. It is calcium hydroxide. Do you know it? The reaction between calcium oxide and water, they will form calcium hydroxide. So it is also commonly found in the natural environment. Okay, so less harm to the environment when you compare with some other chemicals. Is that clear? So a very simple design, it will greatly improve alerts. Questions? Now your turn. In the following minutes, in the following lesson, we come to the calculations from question 2 to question 15. Question 2 to question 15. On your MCs. Take a look on 36. Now, before we let's have a very brief closure of this chapter. You would know any changes in the chemical reactions, okay, in terms of conservation of energy. So usually, we want to talk about heat. It is generated, it may be generalized as this: the chemical energy change to heat. Of course, somebody would think it some work done will be taken into account, but in your delta H calculations, you are going to calculate the heat change at constant pressure, while you treat the work done a negligible term. So we usually do not take too much care about the work done. Of course, if you really want to calculate the internal energy change, that little effect because of work done on the system or on the surroundings will also be taken into account. And then in our lab setting, it is easy understood that if we can measure the temperature change at constant pressure, which means at room temperature, for example, we can calculate the enthalpy change. Do you understand? So they draw, and it can be shown by the pictorial representation by drawing the enthalpy level diagram. The enthalpy level diagram, what is that? We've got the delta H, the H here, we've got reactant and product. So the level of reactant and product, there can be one higher than the other, which will show you this reaction being exothermic and endothermic. For example, this one, I just show it here. Is it exothermic or endothermic? Is it exothermic or endothermic? The one I've shown here. Exothermic. Yeah, exothermic. Yes, that's right. So with the energy level of product lower than that, and the enthalpy level of reactant, delta H smaller than 0, a negative sign. Okay, so once you may also think of a product enthalpy level being high is endothermic. And if you want to explain in terms of bond breaking, a bond formation step, you know that bond breaking requires energy, while bond breaking releases energy. So the exothermic endothermic reaction, you can also think it from an angle, is the imbalance of that two amounts, such so as to bring about the heat being released to the surroundings or absorbed from the surroundings. So we call that exothermic and endothermic reaction respectively. And we have got one more term is called the explanation and the use of standard enthalpy change of reaction. In general, you use the word delta H with the term here with a circle with a with that cross out sign. So once I write it this, which means that this we call it as standard. What are the conditions? What does mean by the standard state? What's mean by standard?
Is standard condition.
Yeah. To be more exact, can you define what is mean by standard conditions?
For
example, temperature.
In room temperature and pressure.
Yeah, room temperature and pressure, 290 Kelvin, 1 atm. Okay, with the solution being 1 molar. So you need to know the standard conditions, definition of it. So thank you. So I've got to carry out the we've got the standard enthalpy change of formation, combustion, neutralization. All those will need some definition. You need some definition of the terms. You carry out the experimental determination of enthalpy changes using the simple calorimetric method. The two design should be noted. One for combustion, one for another reaction involving liquid. The other one just like displacement reaction with a solid and liquid. Do you still remember? So the two design, you have to memorize the design. You may have a chance of drawing this by your own. And finally, after doing some experimental determination of the data, you may use this data for do some data treatment. And of course, you are going to think of some error analysis. For example, heat loss to the surroundings while you do the calculations. Okay, that covers the whole topic. Any part in which you find it difficult? Easy or what? Now let's have a try on MCs. To let me know that you know, right, what is happening here. Have you tried any one of them? All those have not been tried, is it? Okay, let's do it now. Oh, every one of you have a chance of being asked this one. So I would like to call upon those right now on my list. Ngay Trần Thâu. Could you please number 2? And the next one, question 3, I give it to Zhang Siwai. Question 4, Wang Senghian. And question 5, Phong Kai-Hiep. Oh. Question 2. B. Correct. So how would you do the calculations is by using the formula. Heat involved, it is mc delta T. Okay, amount of heat required to warm the water from this. So you may find the M is for water, 1.20 times 10 to the power 6 gram. Water, the specific capacity, 4.18 gram per joule per gram per Kelvin. The temperature rise is on here, which is 18 Kelvin. So you may get the answer as 9.03 times 10 to the power 7 joule, not gram, joule. The answer is B. Okay, is that clear? Now, how about question 3?
Dot.
Oh, yes, that's right. It's D. So mass of ethanol burnt. How you get approach to the problem? You find yep.
153 divided by 13668. Then
Yeah.
10 times
So
the molar mass.
What is that? What is that? This is what you calculate is the number of moles of ethanol burnt. Okay, yes. So you use this as a start. So you times the whole thing 46.0 is because you are going to get that number of moles and then times its molar mass. The similar tricks, thank you. The mass of ethanol, it is just the number of moles of ethanol times its molar mass. Okay, so you may get this 135 over 13468 equals 0.112 mole. So this is 0.112 mole times, what is the molar mass? Sorry, you just mentioned 46, is it?
Yeah.
Just mentioned 46.0 gram per mole times 46. Yo, here comes the answer, 5.14 gram. Okay, thank you. Can you manage? Now, question 4. Wang Senghin. Wang Senghin, are you here? Wang Senghin.
Yes, okay.
Now, while I'm waiting for your answer, shall we move on question 5? Something not requiring calculations. Fong Ga-him. Is it Fong Ga-him? Question 5. Fong Ga-him. Mentioned as D, yes, that's correct. The cold pad, as you know, right? So even though you talk about the dissolution of ammonium salt is generally endothermic. The dissolution, just dissolving. Some of the process is also an endothermic process. So Cyrus, we have also experienced some dissolution of a chemical in water being exothermic. Can you give me some example?
Calcium oxide.
Calcium oxide. It's not dissolution, it's indeed a reaction. So can you think of one dissolution in water being it's not a chemical change? It's just dissolving the salt in the water, being exothermic.
Concentrated sulfuric acid.
Sorry?
Concentrated sulfuric acid.
Concentrated sulfuric acid, yes, okay. Is exothermic. What else? A solid, can you think of one solid dissolving water being giving out heat?
係咪嗰啲 organic acids 嗰啲
？Organic acid dissolving water give out heat.
Calcium oxide.
Sorry, no. 做咩啊 ？Calcium oxide. Calcium oxide is a reaction. It's a reaction water, but not dissolution. Just dissolution is indeed a reaction. the solution. What is mean by that? We have got a solute to formulate the solution, while the chemical nature is just the same. For example, now a ammonium nitrate solid, I add water to form ammonium nitrate solution. So what I want to have this, right? Any other? I should invite someone in the chem lab while you do the preparation info day. Some of you should have known it, or somebody from Science Society.
係咪 potassium hydroxide?
Potassium hydroxide, yes, that's right. Isn't it you are the coordinator, is it? Sodium hydroxide, potassium hydroxide, okay? While you have this, dissolve it in water to form a solution. It is also exothermic, okay? So so as to having calcium compound, dissolving water also exothermic. And for all other ammonium compound, once a dissolved water is also endothermic. Very special pattern, very, very special. And question 4, sorry.
It should be B.
Boy, magnesium. How will you know it? So you check the data. No need to calculate, actually. No need to calculate, actually. Do you know why? You go back to the specific capacity, that definition. What does it mean by that? This is the data. While you talk about the increase per mass of the chemical, if I want to increase the temperature by 1 degrees, 1 Kelvin temperature, so what is the heat involved? Okay, so magnesium is among the others, the largest value, which means that it will absorb more heat than the others, so as to raise the temperature by 1 degrees if you have got 1 gram. Now, no need to take too care of the term 10 grams, 100 joule, 25 degrees. No need to bother. Can you get my point? We just focus on the specific heat capacity of the metal, and you can choose the answer right away. Do you understand? So what is the hidden message? If I have got a material of a higher specific heat capacity, and I do the same process, irrespective of whether metal, non-metal, and other substance, right? If I've got another data higher than this, so it will experience a smaller temperature change. Can you get my point? For example, water. So that's why we will usually say that water is a good cooler. It's because of what? It's in physics, right? It's because water has a very large specific heat capacity. Do you understand? So no need to calculate. Question 6. Question 6. 何孝日。李建樂 please do 7. 黃俊熙 question 8. Question 9 I ask 黃奕朗 for help. Question 6 何孝日。Dot. You mean D? Is it D?
Yeah.
D. Is it correct or not? Now, partly correct, because if you want to talk about product being more stable, generally has a lower enthalpy level. So C or D is a possible answer. But you want to take a look on that product with an enthalpy level being lower than the reactor, which means that the product will no longer hold that energy, so they will release the heat, okay? Heat is released. So which means that according to the conservation of matter, you may put it like this way, the enthalpy level of the reactant should not be equal to the enthalpy level of product, right? But you are going to get that energy lost by as heat. So you are going to think of this relationship between the two. So you may think it like this way. The reactant enthalpy level is higher, but suddenly it drops to lower. Now imagine that you are having a wallet of $1,000, but now you open a wallet, we have got 900, for example. So what is the hidden message? You have spent or lost $100. Okay, you get my point. So of course this is minus, okay? When you compare with the delta H, the definition of delta H, it is enthalpy level of a product minus enthalpy level of reactant. So of course the value should be minus sign. How you understand now?
Yeah.
Yeah. Okay, thank you. So you may get it as the question 7. Who will be the next one?
A.
Lý Kỳ Nội, is it? A. A, correct. A. So how you do the calculations? Tell me. Show me.
Calculate the mole of the glucose first.
Yes, number of moles of glucose. How?
10.0 gram over
It's molar mass.
molar mass.
Yeah.
114 gram per mole.
114. 114, is it 114?
180.
180, 180 gram per mole, a very nice number in which sometimes you can, if you calculate, if you do past paper, right? Some people would even memorize this 0.0556 mole, and I used it to enthalpy change associated with this one. So which means that you are going to times it. Okay, you are going to times it. Okay, so here comes 157 kilojoule. Okay, so you're going to times it, multiply. Okay, is that clear? Because you just talk about per mole. Per mole means per mole of this reaction. Okay, here, per mole of glucose form. So you are going to project this 0.0556 only, so the data should be smaller. Number 8.
D.
D.
C.
C. Okay, C. C is released. How you know that is released for every mole? Release, how you know is released?
The negative.
Negative value, right? Minus sign here, which means that heat is released. Okay, for every mole of SO2 reactant. So according to the equation, kilojoule per mole here means what? Means what? What is mean by per mole? Now, indeed, you may find this one rather got stuck, right? It's per mole of this equation as listed as per the physical quantities. So which means that per mole, some of you may think, oh, per mole, I tried it as 1 mole and per mole oxygen. Now you may think it like this way. Now, which means that per mole of SO2 reactant, it is just a half. Can you see that? Now, because we just mentioned heat is released, so you need not show the minus sign here. No need. Now, because heat is released should be abbreviated by the sign negative, the minus sign. So no need to show it again and again. Okay, if you show it double, which means the another meaning. Question 9, 黃奕朗. Wang Long, are you here?
Yes, I'm here.
Yep.
我睇緊。
好啊. Now, question 10, I would like to invite林俊軒. 11 李晴. 12 is 陳學嘉.
Oh, I know 啦。
You know it? Yeah.
應該就係 boy 嘅。
It's B. It's B. Show me your calculations orally or you just written.
因為佢哋將條式調翻轉啊嘛，咁然之後再將嗰啲 mole 乘個2，咁咪將佢乘翻2，同埋個正負號調翻，即係轉咗正號。
For the reaction, if I write in reverse, the delta H of this reaction should be what? Should be minus, right? Put it with a minus sign. What else have been changed is that this equation, do you see that? It is a reverse of this and all n times 2. Reverse n times 2. Okay, reverse n times 2, minus 1360 kilojoule per mole. Anyone who don't understand, why is it minus 2? Minus is because I put the sign, I reverse the equation from backward to forward to backward, right? So how about the 2? Because the whole equation, with the molar quantities being times 2. Okay, so that's why you use the original data, you flip it. If you flip it that way, it is now this. If you do the thing times 2, okay, so here comes it is times 2. So it is the answer. Do you understand? Now, question 10. Question 10. Yes.
C.
Sorry, A, B, C or D?
C for cat.
C for cat, correct. So enthalpy change of neutralization. So questions delta H3, it is just a neutralization reaction because it involves the reaction between the acid and alkali to form salt and water. So it is truly a definition of delta H of neutralization. Okay. Now, of course, somebody may argue, we have got some exception. Now, ammonia solution and hydrochloric acid to form ammonium chloride. Is it also a neutralization reaction? Now, even though I don't have any water to be formed, is it also a neutralization reaction or it is not?
應該係啊。
It's also a neutralization reaction. Okay, so it will also have its own delta H of neutralization. But at this time, it will be quite contradictory to the definition. You talk about 1 mole of water to be formed. But of course, it is easily understood. If I don't have any water to be formed, you can go back to the thinking of the basicity of acid being monobasic. Okay, you may know that you are talking about 1 mole of alkaline react with 1 mole of acid. You talk about heat involved, any changes involved. Question 11. Question 11. 陳學嘉is it? 李晴嗰個李晴。李晴 11. is A. Now, it's A. Correct, it's exothermic reaction. So because the temperature rise, right? So the greatest temperature rise in the content is 51, but not 45. How we know it's not 45 is 51? What have you done?
我畫咗個即係 extrapolate 咗嗰個 straight line，即係射落去嗰個。
Yeah. So you may have got this. Yeah. Why is it not a straight line? I drawn the wrong. Yes, this one. Yeah. I did not press that yet. And then the second line is on where? Is to draw a slope, okay, which agrees with this, right? Can you see that? The downward trend, but this time I move it here. And what is the vertical line happen? Where will it happen? You draw, but it's not, but you have to lengthen it, right? Lengthen to where? Up to
3分鐘嗰度。
3分鐘 third minute. You may see the word third minute. Because according to the questions, we mentioned it as third minute, the reaction start at third minute. So you draw a vertical line here at third minute here. So the delta H, it is found here. The delta T, sorry, the delta T here is about 51. It's about 51. Okay. Can you find it? Anyone who hasn't got that data, please let me know now. $79 minus is about 20 something. It's 28, right? 28. Okay, being about 51 degrees. So the DSE past paper also have shown this type of questions. Okay, so you need to be highly aware of drawing this. Okay, questions? Now, if not, question 12. Sorry, question 12 is
apple.
A for apple. Good question. Good question for testing your understanding of this delta H of neutralization. How you know it's A?
The number of moles of water formed for both reactions are the same.
Are the same. So which means that in both cases, heat release is the same, isn't it?
Oh, right.
Yes, that's right. So how would you know the delta T? Delta T you are going to calculate as M0 delta T. Is there any change about the M? Is there any change about the M? This one depends on the number of moles of water formed. Okay. So for both cases, you are mentioning these two, the both cases, the number of moles of heat, the water will form will be the same. So the same heat will be evolved. Okay. How about the mass of the solution? Originally, what is the mass of the solution? It's 10 grams plus 10 grams, 20 grams. To have got certain type of heat, right? But this time, what's the next case? It is 20 grams plus 20 grams. It is 2 times larger, right? So if you have got the same heat release, but the the solution that with the mass being doubled, what will happen to the delta T? Is it the same? Is it the same?
個 E 等於 MC delta T 個 M double 咗個 E 就變咗少一半。
So how about delta T? That it will be half, right? Okay, the delta T will be half. You understand? Anyone who don't understand? For those who understand, please put up a hand. Not understand, please put a cross. Very important questions. This one, very, very important. Put a star here, very important. I usually ask this, right? You may know in the past paper. Just one tick, one cross, latent cross. How about the others? Understand or not? 唔明。Now, 好。Anyone who you can turn on the mic and try to explain how will you get that problem, get approach to the problem again. We've got two cases, right? Now, indeed, for this type of reaction, we've got delta H neutralization minus 57 point something. So, of course, you can do that calculations by yourself. Okay, and you can trace back what is the heat evolved and what is the temperature change, etc. Okay, but we try to skip it. This time we skip it. It's because you are talking about the same reaction. So the per mole of water will be formed, it will release the same amount of heat, right? So you focus on calculating how many moles of acid and alkaline respectively. You know that they are just perfect match 1-to-1 mole ratio they react. So you may have the same number of moles of water to be formed, which means they have got the same amount of heat it will be given out. Now that type of heat will be elicited by those solutions to experience a temperature rise. Can you get the point? So the same amount of heat, we have got a certain volume of water. Okay, for example, 10 plus 10 is 20 grams. Of course, they will experience a temperature rise. But this time I multiply, okay, I double the amount of solution. So will they experience the same temperature rise? The answer is no, because there will be more solution that will have, okay, involving that experience the heating of being heated. So that's why you have got that calculations. The heat evolved, it depends on the mass of the chemical as well as the specific capacity and the experience by the temperature rise. Maybe I put it this way. Somebody will still don't understand. I'll give you another analogy. For example, I give a very hot object and I put it into the certain volume of water, a very hot object. So you are going to measure the temperature rise here. So of course, the temperature will rise. Okay, what will happen? If I have got 200 cm cube of water with the same hot object, with the same heated to the same temperature, I put it inside and I do the measurement of delta T. Would they have the same temperature rise? Listen, do they have the same temperature rise?
No.
No. So what is the difference between that two, delta T?
The mass is the mass of the 200 cm one is twice that one, so the temperature rise should be half of it because the heat is more distributed within the solution.
Yes, that's right. So that's why whenever if you have got chemical burns, I ask you to wash your wash affect area under running water, but not still water. Can you get my point? You are going to flush it under running water because I want to make the mass of water as large as possible. Okay, such that the heat will be much transferred from the finger to the water. Okay, with full speed. Do you understand? So it is something about question 12. I hope all of you would understand what is happening. Something about chemistry here, something a little bit about physics, and this is totally about physics. Do you realize? Question 13. Who else? Who else have been answered here? Tần Chuẩn Hay.
D. Dot.
D. Dot. Okay, so endothermic reaction. Endothermic reaction. Yes, that's right. So this part, the endothermic, because the graphite, it is the stable form. It's a standard state. So the electrolysis water involving breaking of bond, while the sublimation of dry ice involving solid to change of physical state from solid to gas, in which intermolecular force to be overcome. Okay. The final two questions, 14. And 15 Cyrus again.
Dot.
14 dot. Yes, that's right. Exothermic. This one, you know it. This is displacement reaction. And this is neutralization reaction. So these two also gives out heat. The last one, 15.
A.
Yep, A, that's right. So the formation of water is minus 0.5 formation, which means you are going to have this. This reaction. So when you compare with this and this, it is just the reverse. And what? And this one being half. Okay, can you see that? It's being half. So we have got half, 1, 1, and you have got this. So this is delta H being minus 0.5 X kilojoule per mole. Okay, now is it clear? So we just stop it here. And in this weekend, I would like to ask you to do some long questions to let me understand that you know how to do the calculations in written. Okay, so you will see the homework posted onto the Google Classroom and please finish during this weekend. Okay, before you leave, could you please give me the understanding? Okay, today. After sorry to say that, it's not reset. Sorry about that. Now let me know the number before you leave. Thank you. Almost 6, 7, and 8. Yeah, thank you. For those who have typed the number, you may now leave. Thank you. Bye bye. Wait, say goodbye to me. 喂，冇禮貌你班友。拜拜拜拜。咪咯。